Hey everybody, welcome back, and we're going to be talking about our last few key features today. So this is wrapping up the entire chapter, talking about functions and transformations and the different qualities and characteristics that you can use to describe a graph. And so starting out these notes, we have 4 different graphs, and all I want to do to get things going is just to compare and contrast them. So what are some of the things that are similar between all 4 of these different shapes? It doesn't have to be that complex, so you could talk about how they're all curvy or wavy. That's fine. Each of the graphs have relative maximums or minimums. They all go positive and negative above and below the x-axis. And so one of the reasons we're doing this is to get you to think critically about the vocabulary that you've learned so far. There are probably lots of other characteristics that they share in common, but those are the ones that stood out to me at least. Now what about some differences? All of these graphs are unique, they're not the same. And if you're looking here, B and C have end behaviors that are going in opposite directions, which is kind of interesting, versus A, the left-hand side and the right-hand side, the y values go to positive infinity. They're going in the same direction. The end behaviors for D actually are really weird because it just keeps going left and right forever. It's actually trapped between a floor and a ceiling. So another difference you could talk about would be their range. So the range for D is limited and the range for the other 3 are unlimited. Another difference is that they don't all go through the origin, and that's actually kind of an important thing here later on. Just like with similarities, there are plenty of differences that I probably haven't talked about or noticed, and that's why it's good for you guys to try to think of different traits there as well. So let's go down below and talk about the vocabulary. These words are going to go back up to those 4 graphs, and we're going to see visualizations of them. So this trait, this characteristic, deals with symmetry. What is symmetry? Symmetry is just when a graph looks identical to its original after a flip or reflection or a rotation. Now symmetry is crucial to being admitted into one of the following 2 groups. These groups are called even functions versus odd functions. Now, this is not like even and odd numbers, but there are some parallels. There's a reason that mathematicians chose these words. So what would be true about even numbers? Well, anything that's even is divisible by 2. You can chop it into 2 equal-sized halves. And that's important because odd things don't do that. They're a little bit more awkward, and so one half is larger and the other half is smaller. They're not halves, okay? And so odd things are a little bit more lopsided. When it comes to being an even or an odd function, though, even functions have a graph that is bilaterally symmetrical across the y-axis. I like to think about this as almost being like a face. If you take the left-hand side and the right-hand side and you reflect them across this central axis, this y-axis in this case, it would look exactly the same. At least that's our ideal thought about the human face. So anything that on the left and the right, when you flip those 2 sides, ends up where the original was, is classified as being an even function. So look up above at the 4 different graphs. Is there anything where the left and the right of the y-axis can be exchanged or reflected to look like the original? I think A is really the only one that does that. Now, if we had taken that graph and moved it up or down, it still is considered even because the left-hand side and the right-hand side are still mirror images of each other. B, C, and D don't really do that. If you flip those graphs, they don't end up where they originally started. So that's kind of weird. That actually introduces us to our next group, which are the odd functions. So odd functions have graphs that are rotationally symmetrical about the origin. Now there are some very important reasons why we have to be across the y-axis and around the origin. There are 2 tests that mathematicians use to confirm if things are even or odd. And while we aren't going to be doing those tests, it is an important thing that you can't just be rotating around any point or rotating across any axis. That doesn't qualify you to be even or odd. So which of the 4 functions might be considered odd functions, rotationally symmetrical? Well, if we look at B, if we were to rotate that 180 degrees, it falls perfectly on top of its original. If we did C and rotated that about the origin. That's like a propeller that's been off kilter. It's not going to land on top of where it originally started. Okay? If you were able to take that rotation point and move it to the point of inflection on that curve, then it might be seeming like an odd function, but we have to use that rotation point when it's stuck on the origin. Now D, I know we can't see the full graph of D because it continues forever, but D is considered odd in this case. If you were to rotate it, that hill would rotate down and become a valley, which that's what's happening over there on the other side. So the only two graphs here that are considered odd functions are B and D. C falls under this family of being in neither group. Man, many functions are in the neither category. It's hard to be even or odd. Again, it has to pass those two tests, which aren't easy. Below the terms of even or odd function is this idea of period. Now, a period is when a graph repeats its pattern over a set distance of x values. So it means that the graph would be cyclical. It happens in cycles over and over and over again. And so we're wondering, how long does it take before the cycle repeats? Now, the only graph that has a period up above is D. And if you look at how the graph starts, it goes up and then down and then up. And then it repeats up and then down and then up, down, up. It's that wave over and over and over again. And if we look at the scale on the x-axis, how long does it take before we repeat that up, down, on pattern? Well, it's not quite 3 units. It's a little bit more than 3. And if you have to think about a very famous number, a little bit over 3, that would be pi. Pi is intricately woven into this graph. It's a sine graph, and you'll learn more about those in pre-calculus. But every pi amount of time, every pi units, is going to repeat. The rest of the notes are fairly easy. They go quickly because we're just identifying things as being even, odd, or neither. So let's look at the questions below. Number 2, for the first graph, graph A, if we are trying to see if that's even, it doesn't flip left and right and fall on top of itself. If we're trying to see if that's odd, we have to almost rotate that in our head around the origin, and that would fall on top of the original graph. So this qualifies as being an odd function. Graph B, if we try to see if that's even, it would not flip back onto the original. If we try to see if it's odd, it does not rotate back on top of the original without doing a whole loop, which that's kind of pointless. So this graph is neither. It's not even, it's not odd. If we look at the third graph, graph C, this is definitely even. If you look at the left and the right sides across the y-axis, it's bilaterally symmetrical. Hopefully that gives you a little bit better of a taste for what we're looking at and looking for. Even and odd functions, this terminology gets used again later in the year, but there's a little twist on it. Even and odd actually has something to do with the equations that they're coming from, but I don't want to give too much away. Let's look at the back. All we're doing on the back is determining if it's even, odd, or neither. So graph 3, definitely even. It's left and right bilaterally symmetrical across the y-axis. Graph 4, this is neither. You can't flip it horizontally or rotate it around the origin to get it to land back where it started. Graph 5 is odd. This is an unusually hard one. Lines can be tricky sometimes, but if you rotate that around the origin like a propeller, it's going to land right on top of itself. 6 is neither. 7 is an even function. It's actually very similar to the graph on the front. 8 is neither. 9 is an odd function. Now I know that there are 2 parts to this, but if you rotate it around the origin, the top right will land on the top left, and the top left will land on the top right. So that's an odd function, rotationally symmetrical. 10 is also odd. And then 11, one of the weirdest graphs that we have on the back. It's called a step function because it looks like steps. But if I go ahead and I flip it, trying to see if it's even, it doesn't fall on top of itself. If I rotate it, remember that rotational point is at the origin, it's not going to fall on top of itself. If we could move that rotation point, we would have to move it down in between two of the steps in order for it to be able to rotate into a position that the original was at. And that doesn't work. The rotation point has to be the origin, so this is neither even nor odd. Down below with the last question, I'd like for you to try to draw a graph of an even function, an odd function, and then something that doesn't satisfy either of those requirements. And do something different than the notes. Try to push yourself and expand your thought process on what even and odd things can look like. I hope this video helped. And again, we've been talking about all these different vocab terms to describe graphs. This is just one other way to describe what things look like. If you have any questions, please feel free to contact me, and I'll do my best to get back to you. And take care, everybody. We'll see you next time.